In this video, I'll be discussing nuclear magnetic resonance, or NMR spectroscopy. NMR spectroscopy is a type of absorption spectroscopy. The light absorbed by molecules in NMR spectroscopy lies in the radio wave region of the electromagnetic spectrum. This is the very long wavelength region of the EM spectrum. We'll sometimes refer to the light in this region of the EM spectrum as radio frequency or RF radiation. In NMR spectroscopy, when RF radiation is absorbed by molecules, what happens is this: the natural spin of the nuclei of certain atoms is affected. Now, we'll have more to say about this later on. Here we have an example of an NMR spectrum. In the spectrum, there are signal peaks, each peak located at a different RF frequency. As we'll learn, an NMR spectrum of a compound provides an enormous amount of information about the compound's molecular structure. Actually, even more information than we normally get from UV-Vis or IR spectra. A nucleus of an atom is a ball of positive charge. Many nuclei spin on an axis. The spinning motion creates a magnetic field, and as a result, the spinning nucleus behaves like a tiny bar magnet. The direction of the magnetic field of the spinning nucleus can be predicted using a right-hand rule. Let the fingers of your right hand curl in the direction of the spin of the positive charge with your thumb extended. The tip of the thumb corresponds to the north pole of the bar magnet. Now, you'll recall from general chemistry that an electron has a -1 charge. It's a -1 charged particle, and it's known to act like a ball spinning charge. It spins in two possible directions, clockwise and counterclockwise. Quantum mechanically, its spin characteristics are stipulated by a so-called spin quantum number. A spinning nucleus is similar. Its spin properties are stipulated by a spin quantum number I. The value of I specifies the number of directions that a nucleus can spin. For example, if I equals 0, the nucleus has no spin. If I equals 1/2, the nucleus spins in two directions, clockwise and counterclockwise. If I equals 1, the nucleus spins in three directions, clockwise, counterclockwise, and a spin direction in which the spin axis is perpendicular to the spin axis of the clockwise and counterclockwise spins. As it turns out, the spin properties of a nucleus depend on the oddness or evenness of the number of protons and neutrons in the nucleus. If the mass number of the nucleus is odd, then whether the number of protons is odd or even, I will have the value 1/2. If the mass number is even, there are two possibilities. The number of protons are odd or even. If the number of protons is odd, then I will have an integer value, 1, 2, 3, and so forth. If the mass number is even and the number of protons is even, then I equals 0 and the nucleus does not spin. Let's suppose that we have a set of spinning nuclei. All the nuclei have an I value of 1/2. Now, in the absence of any magnetic field, the spinning nuclear magnets are randomly oriented. However, suppose we place our set of spinning nuclei in a magnetic field. The spinning nuclei will arrange themselves in two orientations, one in the same direction as the magnetic field. Here we say the nuclei have a with field orientation, and the other in the direction that is opposite to the magnetic field. These nuclei are said to have an against field alignment. Nuclei that have the with field alignment have a lower energy than the nuclei that have the against field alignment. It turns out that slightly more than half of the nuclei will have the with field alignment, and slightly less than half of the spinning nuclei will have the against field alignment. Let me try to make this clear by using some everyday objects, a bar magnet and a compass needle. A compass needle is a bar magnet that can freely pivot. The head of the arrow is the North Pole and the tail end is the South Pole. Let's take a compass needle and place it next to a powerful bar magnet. The compass needle will naturally orient itself so that unlike poles are together. That is, the north pole of the compass needle pointing towards the south pole of the bar magnet, and the tail end, the south pole of the compass needle, pointing towards the north pole of the bar magnet. Here we would say that the compass needle has the with-field alignment. Now suppose we rotate the compass needle 180 degrees so that like poles are together. The north pole of the compass needle points towards the north pole of the bar magnet. The compass needle is going to be under a constant tension. It's going to feel a constant force that tends to push it back into its with-field alignment. Here we say that the compass needle has an against-field alignment. The potential energy of the compass needle in the against-field alignment is higher than the potential energy of the needle with the with-field alignment. The difference in energy between the spinning nuclei, that is, between the nuclei that have the with-field and those that have the against-field alignment, depends on the strength of the applied magnetic field. This energy difference we give by delta E. It's proportional to the strength of the magnetic field. Delta E is proportional to and varies with the strength of the external magnetic field. The stronger the magnetic field, the greater the difference in the energies, the greater the value of delta E. The weaker the magnetic field, then the smaller the energy difference, the smaller the value of delta E. We can express this relationship more precisely with an equation. Here, equation 1. This delta E will equal gamma times H times B over 2 pi, where B measures the strength of the applied magnetic field. Gamma is a proportionality constant. It's called the magneto-gyric ratio, and its value depends on the nature of the nucleus. The H that we have here is Planck's constant, and of course pi is pi. This equation expresses the idea that the difference in the energy between our with and against field spinning nuclei, the delta E, is directly proportional to the strength of the applied field, given by the symbol B. If we raise B, we raise delta E. If we double B, we'll double the energy difference delta E. When electromagnetic radiation is applied to the nuclei that are placed in a magnetic field, and the energy of the RF photon matches delta E, radiant energy is absorbed. The nucleus in the with-field alignment jumps to the higher energy level, namely the level corresponding to the against-field alignment. This jumping from one alignment to the other, the nucleus virtually flips from one alignment to the other. When the nucleus flips its alignment, it's said to be in resonance with the applied RF radiation. When spinning nuclei are placed in the magnetic field, there's another type of motion that occurs. The magnetic axis of the spinning nucleus will wobble about the axis of the external magnetic field. This wobbling motion is similar to the motion that a spinning top has when it gradually loses its energy. The wobbling motion is called precession. When an RF photon is absorbed by a precessing nucleus in the with-field alignment, it will cause the nucleus to flip to the against-field alignment. Absorption of the RF photon occurs when the frequency of the RF photon equals the frequency of the precessing nucleus. That is, when new RF photon, the frequency of the RF photon matches the frequency of the precessing nucleus, the spinning nucleus flips, resonance occurs, and energy is absorbed. For any spinning nucleus in a magnetic field, let's write equation 1 again. Now we already know that delta E is the energy of the photon that's absorbed that causes the nucleus to flip its orientation. Delta E, the photon, is always equal to Planck's constant times the frequency of that photon. Delta E photon equals h nu RF photon. Now if we combine these two equations, we get this equation. Frequency of the RF photon is equal to gamma times b over 2 pi. Moreover, at resonance, as we've already indicated, the frequency of the RF photon equals the frequency of the nucleus. We can substitute the frequency of the nucleus for the frequency of our photon, and we generate what we call equation 2. And equation 2 is important and useful because it's a way to mathematically express the frequency of the precessing nucleus with respect to the strength of the magnetic field. The frequency of the precessing nucleus equals our proportionality constant gamma times the magnetic field strength B divided by 2 pi. A comment about the values of gamma, the magnetogyric ratio. It depends on the nucleus. We're going to be examining the NMR of two nuclei, H1 and C13. H1 is the most abundant isotope of hydrogen that occurs naturally. C13 is the less abundant isotope of carbon. It's present naturally about 1%. For H1, the gamma value is equal to 2.68 times 10 to the 8th radians per second Tesla. Tesla is the unit that's used to measure magnetic field strength. For C13, gamma is 6.73 times 10 to the 7th radians per second Tesla. Now, let's consider two types of bare nuclei, an H1 nucleus and a C13 nucleus. The bare nucleus is going to absorb at a frequency that's predicted by equation 2. If you have a bare proton, a bare spinning proton, equation 2 tells us that it will take a frequency of 100 megahertz to flip the bare proton in an applied field of 2.33 teslas. If you have a bare C13 nucleus, equation 2 tells you that a frequency of 25 megahertz is needed to flip the bare C13 nucleus in an applied magnetic field of 2.33 teslas. Or put differently, if we have our external magnetic field with 2.33 teslas for a bare spinning proton, the frequency of the spin of the precessing proton will be 100 megahertz. The equation 2 will tell you that. If our magnetic field, again 2.33 teslas, and we have a spinning C13 nucleus, the equation will calculate that it has a natural frequency of 25 megahertz. If all the nuclei of atoms in molecules behaved like bare nuclei, the nuclei would all resonate at the same frequency, and the NMR spectrum of a compound would yield just a single peak. There would be no information. Fortunately, that's not the case. Atoms in molecules will resonate at different frequencies, producing different signals in the NMR spectrum. And here's why. Atoms and molecules are enveloped by clouds of electrons, either bonding electrons or unshared electron pairs. When placed in an external magnetic field, a force will be applied to these electrons. This causes the electrons to circulate essentially in the same plane and in the same direction. They become like race cars all traveling the same direction around the racetrack. Now there's a fundamental tenet of physics. When a charged particle moves, it produces a magnetic field. The circulating electrons, moving as they do, will produce a secondary magnetic field. This secondary field will always be oriented so that it is opposed to the direction of the applied magnetic field. Now the result is this. It causes the net magnetic field that's experienced by the nucleus to be weaker than the applied magnetic field. You see, the secondary magnetic field of the circulating electrons subtracts from the applied magnetic field, producing a smaller magnetic field that's experienced by the spinning nucleus. In general, a nucleus surrounded by electrons is said to be shielded or screened by the electrons. The greater the density of the electron cloud about the spinning nucleus, then the smaller the net magnetic field will be that it experiences. Now suppose that we place an atom in a molecule, the nucleus in the atom that's in a molecule, and a bare nucleus. And they're each placed in a given external magnetic field. The net magnetic field felt by the nucleus of the atom is going to be less than the magnetic field felt by the bare nucleus. And this is called the chemical shift effect. Chemical shift effect. The net magnetic field felt by the atom's nucleus is less than the applied magnetic field by a fraction. Use the symbol sigma. Now, given that, we can calculate the net magnetic field experienced by the spinning nucleus, the nucleus that's enveloped by clouds of electrons, namely using this equation. It equals the strength of the applied magnetic field minus the sigma value times the strength of the applied magnetic field. Well, it turns out there's a limitation in NMR spectrometry. An NMR spectrometer measures the frequency of spinning of precessing nuclei. But an NMR spectrometer cannot accurately measure the actual resonance frequency of a spinning nucleus. However, it can measure accurately and precisely the mathematical difference between two different resonance frequencies. What's routinely done in NMR spectroscopy is this. A chemical agent is added to the sample being analyzed. This agent functions as an internal reference standard. It provides a fixed resonance frequency signal that can be compared to the resonance frequencies of all sample nuclei. Now, the reference standard that is always used for all NMR spectra is an organosilicon compound called tetramethylsilane, or TMS for short. Here's its chemical structure. 4 methyl groups on a central silicon atom. This compound has been chosen as a reference standard in NMR because the resonance frequencies of the nuclei are lower than the resonance frequencies of the nuclei in the atoms of organic compounds. For each nucleus in the sample, the NMR spectrometer measures the resonance frequency difference given by this expression, nu nucleus minus nu standard. All right, however, there's still a problem that has to be resolved. This value, the resonance frequency difference between sample nucleus and standard, will depend on the magnetic field strength that the instrument functions at. Different instruments function at different magnetic field strengths. Consequently, different spectrometers would yield different values of this frequency difference for the same sample. That could create significant disorder when one is trying to communicate the results of an NMR for, say, your instrument versus somebody else's instrument. Well, the solution to the problem is as follows. Each spectrometer has what's called a fixed instrument frequency, or nu naught. Nu naught is defined according to our equation 2 we saw previously. Nu naught equals gamma times the strength that the instrument operates at, the applied magnetic field strength, divided by 2 pi. So the instrument knows the value of V naught, the strength of the magnetic field, and it can easily, with its computer, calculate the value of nu naught. What it next does is to take this resonance frequency difference, nu nucleus minus nu standards, and divide it by nu naught. When it does this, it obtains a value which is independent of the spectrometer, given here by equation 3. However, there's still a problem that remains. namely this. The typical values of the equation 3 ratio are very, very small. For example, an alkyl proton's value is around 0.000015 units. Very small, inconveniently small. To correct this, what we do is we always multiply the ratio expression in equation 3 by 10 to the 6th. This will raise values to a convenient range. Most H1 NMR values are between 0 and 10. At this point now, we have a resonance frequency related parameter that can be used to locate signals in an NMR spectrum. This is called the delta parameter, or also the ppm parameter. And it's given by this expression. It's our equation 3 ratio times 10 to the 6th. The range of the observed delta values for H1 NMR, proton NMR, is 0 to 15 parts per million. For C13, the range is wider, 0 to 340 parts per million. Here we see an actual proton NMR spectrum of a compound, methyl iodide, CH3I. There is one signal peak for the 3 hydrogens of methyl iodide at about 2.1 ppm. Now there's only one peak because the 3 hydrogens of the methyl group are equivalent. NMR samples are almost always in a liquid or solution state. In this state, the molecules spin and tumble so rapidly that they're in the same environment when averaged over time. You also see a second signal peak at the far right. This is due to the TMS protons. TMS is the added standard. Now we always add TMS to an NMR sample, and we always see a TMS peak in every NMR spectrum. It's always the rightmost peak in the spectrum because the TMS nuclei are in the densest electron cloud environment. And this is due to the lower electronegativity of the silicon atom compared to carbon. Because of this, the net magnetic field at the TMS nuclei is lower than that of all nuclei in organic compounds. Remember, when the net magnetic field is low, the frequency of the spinning nucleus is also low. So in an NMR sample, of all the spinning nuclei, including organic sample molecules and TMS molecules, the TMS nuclei spin at the lowest frequency and will always have the lowest delta value. Now procedurally, when an NMR spectrum is generated for a sample, the TMS signal is located and always set to 0 frequency, as well to 0 delta, 0 ppm. This is done either manually or by computer. We also note that this particular spectrum was created with a 60 megahertz instrument. The internal frequency of this spectrometer is 60 megahertz, 60 times 10 to the 6th hertz. Now it's interesting that even if you weren't given this, by examining the data in the spectrum, you can logically deduce this value, 60 megahertz. Let's take a look. Well, from the spectrum, you can see that the frequency difference between the methyl frequency and the frequency of the TMS is about 125 hertz. You can see that here, TMS 0. When you look at the value of the methyl frequency, it's about 125 hertz. From the spectrum, we read the value of delta for that signal, and it's about 2.1. You can see that here, at 2.1. The mathematical expression that defines delta is given here. All right, if we substitute 125 hertz for the frequency difference in the numerator, we arrive at this expression, we have one unknown, nu naught, fundamental frequency of the instrument. We can then solve for it. And if we do carry out the arithmetic, nu naught comes out to very close to 60 times 10 to the 6 hertz, or 60 megahertz.